Hello everyone, my name is Sepehr Ebadi. I'm a Pappalardo Fellow here at MIT, and today I will be telling you about how we plan to use radioactive molecules as probes for fundamental physics. Let me tell you this story that is very dear to my heart. It all goes back to Shelter Island Conference in June of 1947, where some of the brightest minds in physics had gathered at the time. This gentleman, Willis Lamb, who happens to be my academic grandfather, came to this meeting with some fresh out of the data oven that he'd published about only 2 weeks after this conference. He had done new measurements on the spectrum of the humble hydrogen atom. We know that the energy levels of a hydrogen atom, even from the days of Bohr, they are quantized. For example, the n equals 1 to n equals 2 levels are separated by UV light. But if you zoom in, there is something called the fine structure within this that arises from relativistic effect and angular momentum. And even this at the time was very well understood using the Dirac model. But here there's two levels, 2s half and 2p1 half. The models at the time predicted they should be the same energy level. However, Willis Lamb observed a huge energy separation between them of about 1 megahertz. It's important to note everyone circled in red here actually participated in the measurement indirectly. They were here at MIT in the radiation lab developing microwave technology for the war effort, and these technological advances at the time led to this discovery. Anyways, going back to the story, this shift was the hot topic of the conference. Where does this shift come from? Bethe, along with some of the colleagues here, came up with the explanation during the conference, and on the train ride back home, Bethe writes this paper. It all goes back to the shape of the orbitals. In the s orbital, the electron actually gets very close to the nucleus. It goes very, very quickly when it's around the nucleus, very close to the nucleus. And you can think of it as a little particle accelerator within the atom. In this relativistic environment, the many particles pop in and out of existence, but because of the conservation of the energy, when the particle gets up further away from the nucleus, they disappear. But this tiny effects of particles popping in and out of existence modifies the interaction between the electron and the nucleus. However, the same thing does not happen in a p orbital because, as you can see, the electron does not actually spend any time near the nucleus. So the techniques to understand this and do these calculations, and also having the vision that particles can pop in and out of existence, was the birth of what you could consider the grandfather or even the standard model as what we know it. But there are many more lessons we can learn here. One is that the precision spectroscopy of atoms and molecules tells us about the high energy physics that govern their constituents. And maybe another personal lesson, as both a nuclear and AMO physicist, there are tremendous opportunities when AMO physicists and nuclear physicists collaborate. So I think to recreate discoveries like this, we should all collaborate more. Despite many decades of progress and incredible triumphs in physics, the standard model is still incomplete. There are many puzzles out there, for example, what is dark matter, why is the strong force a little bit weird, and many more. But here I will focus on one question. Why is there more matter than antimatter in the universe? And it turns out this question might provide insights to the answer and answers to the previous two problems that I mentioned. To understand the problem, we first need to know the story of the universe. First, there was the Big Bang. We think there are equal amounts of matter and antimatter produced. They annihilate to create photons, and some of these photons we can see, for example, in the cosmic microwave background. But turns out a tiny bit of matter was left behind that was not fully annihilated. This created the stars, the planets. We came along and we're building instruments to look back and answer this fundamental question. Where do we come from? What causes this asymmetry between matter and antimatter that led to our existence? But to first understand this asymmetry, let's have a crash course in fundamental symmetries and their role in this matter-antimatter asymmetry. Consider a scientist with a clock and a ruler. That's all you need to do science. The first symmetry that we want to discuss is called charge conjugation. We ask the question, if this scientist was made of antimatter instead of matter, would they observe the same physics? The second one is parity. If I reverse the direction, or imagine if you have an Australian scientist, would they observe the same physics? Last one is time reversal symmetry. If the direction of motions was reversed, would I observe the same physics? Note that here I'm not talking about macroscopic time or notions of entropy, but microscopic time that governs the fundamental interactions. These are discrete symmetries of our physics, and turns out if you need a process that favors matter production over antimatter, a combination of C and P symmetry have to be broken or violated. Turns out CP violation already exists in the standard model, but just not enough, and by a lot not enough. Going back to the land of particles, let me tell you how these symmetries govern the physics of individual particles. Imagine you have your scientist again with a fundamental particle. Let's say this particle has a charge and it's spinning. We know particles have something called the spin, and you can think of it as if it's a ball of charge rotating, and you get the magnetic dipole moment, which is the spin. But imagine if this particle had a slight deformation of its charge distribution. Now you would have what's called an electric dipole moment, which quantifies the distribution of this charge. Now let's look at the same scientist in a CP mirrored universe. First, let's apply this charge conjugation symmetry transformation. Now you have a scientist made of antimatter and a negatively charged particle. And now apply the parity. If I calculate these moments, you see the magnetic moment is actually pointing along the same direction as the scientist, same as before. But in this CP mirrored universe, the electric dipole moment is pointing away from the magnetic moment. So if a permanent electric dipole moment exists for a particle, this means that we live in a universe that CP symmetry is broken in it. This is extremely powerful. So by finding these EDMs, electric dipole moments, we can find sources of CP violation. And how do you go about measuring it? Imagine if you have no electric field, up and down pointing of the dipole moment don't have the same energy. If I apply an electric field, I split these two and I can measure this. And to find an EDM, first you have to look for large intrinsic dipole moments, maximize the electric field that you apply, and increase your energy resolution. We'll get back to these three criteria later. The search for electron EDMs has been going on for quite a while in atoms and molecules. In atoms and molecules, you have electrons, for example, and there are two processes that can give rise to an EDM in an electron. The electron itself can have an EDM, or in an interaction with the nucleus can give rise to an EDM. The case in the nucleus is actually quite more exciting. You have protons and neutrons, they exchange pions, and inside of protons and neutrons you have quarks, they exchange gluons, so you have so many different processes that can give rise to an EDM. And you can group them all together into one nuclear EDM that you go and measure. People have been at it for quite a while. Some of the most extremely precise measurements of humanity have been measuring this electric dipole moment of the electron. But in some sense, you can think of it, that's like buying an individual stock. That the price of any individual stock could go up or down. The same thing with the electron, because there's so few things that could give rise to an EDM there. You might get lucky and find it, and you might not. But because the nucleus is so prolific, there's so many things going on in there, it's like a diversified portfolio. So you're bound to see something. Another way we can quantify the energy reach or the power of the search of these EDMs is ask the following question. If a high energy force or particle couples to the nucleus to induce this EDM, what is the mass of this unknown particle? And to help illustrate that, I have this plot where on the y-axis, we have the limit or the measurement of this new particle mass, and on the x-axis, we have the limits, we have the dates that some of the discovery were made. This band over here is There, thanks to LHC's direct observation and electron EDM measurement, meaning we've searched up to this energy and we did not find any excess CP violating new particles through an EDM search. And up here, you remember I told you the standard model actually predicts a certain amount of nuclear EDM, but just not enough. And what this means is that if you go to very, very high energies, the standard model tells you that there should be an EDM there. So, but we know there is more EDMs, there's more CP violation in the universe because of the fact that we exist. So there has to be something in between in this discovery window. So this is a really exciting opportunity that you can close a discovery window and you're bound to find something. People have been at it for a while, for example, measuring neutron EDM. People have measured the EDM of of atoms and even molecules. But no one has ever been able to really push and make significant advances in this discovery window. And our tool to go there is radioactive molecules. We call them amplifiers of the CP violation. Remember these criteria. To find an EDM, first we need to look for something with large intrinsic dipole moment. And the way we do that is through radioactive molecules. It turns out some radioactive nuclei like francium, thorium, radium have a pear-shaped nucleus. It kind of looks like a pear. And this increases the intrinsic dipole moment by about a factor of 1,000 compared to spherical nuclei like mercury that have been studied previously. Then if you put this nucleus inside of a molecule, you get access to electric field that are 10 to the 6 times or million times larger than what you can apply in a lab. And lastly, if we throw at it wonderful techniques that are developed in the past few decades in laser cooling and quantum control, we can really enhance the energy resolution and even reject systematic noises. And through this amplification chain, we hope that we can turn CP violating interaction to a detectable EDM. Going back to this plot, we can really put some numbers down and see the power of this platform. If we get a single molecule and only have 100 milliseconds of coherence, that's less than you can blink, and take data for 2 weeks with these conditions, you already reach limits imposed by the LHC. If you hone your tools a little bit, trap 1,000 molecules, half a second of coherence time, and take data for 2 weeks, you reach nearly 100 tera electron volts. And lastly, if you get to about 10,000 molecules with 10 seconds of coherence and a year of data, you can close the discovery window. While these numbers seem really daring, I want to highlight that these are already demonstrated for non-radioactive molecules. For example, here at MIT in the labs of Professor Ketterle or Professor Zuerlein, they routinely do experiments with thousands or hundreds of thousands of these molecules with long coherence times. So we just have to do it with radioactive molecules. I mean, how hard can it be? The molecule that we want to choose is Radium X, and I will tell you the naming. Radium is in the second column of the periodic table, so it has 2 valence electrons. So the simplest molecule you can make with it is if you bring a ligand to it that has a valence hole in its shell. The electron from the radium goes there and forms this molecule. So you're left with a lone electron away from the bond. So this is essentially as hydrogenic as a molecule can get. And you can talk to this electron without disturbing the bond, and this is a very well-behaved molecule. Turns out because of the large electronegativity inside this molecule, you have extremely large electric fields, even further enhanced by the relativistic effects due to heavy radium nuclei, nearly 100 gigavolts per centimeter. And lastly, it doesn't really matter what ligand you choose. You can, for example, pick a fluorine, an OH, an NH2. It doesn't change the physics, but it allows some cool opportunities for in quantum engineering of the molecule for some cool tricks. Radium has a few isotopes, the famous one being radium-226 that was discovered by Pierre and Marie Curie and is used in glow-in-the-dark paints. This has no nuclear spin and it lives for about 1600 years. This is an ideal isotope for us to prototype laser cooling and trapping. And also, Because it has no nuclear spin, we can actually do an electron EDM measurement with this platform. There are two other isotopes that have nuclear spin that we would use for a nuclear EDM measurement, but they're extremely short-lived and very, very, very radioactive. But here in our group, epitomized by this beautiful paper in Ronald's PhD, we know how to produce them, we have done spectroscopy on them, and we even have devised laser cooling schemes for them. So we feel very confident in embarking this journey toward laser cooling of these molecules. This is a schematic overview of laser cooling. You have the molecules produced in a buffer gas cell in a very violent process called laser ablation. At around 10,000 Kelvin, with cryogenics, we bring them down to 2 Kelvin. We laser cool and slow them down and trap them with a combination of magnetic and electric fields. We then apply wonderful techniques in AMO physics called like Doppler cooling and trapping to them to bring them down to fractions to only a few microkelvin. And when we trap them in these optical potentials, then we can do an electric dipole moment measurement with them. This has been a very well established technique that has been done with many stable isotopes, and any one of these folks would tell you production and slowing is the hard part. Once we learn how to do that, we're golden, and this is the easier step. So in my postdoc, I hope to focus on production and slowing of the molecules. All of this happens in the buffer gas cell. Inside here, you can see it. This sits in a vacuum chamber at 2.5 Kelvin. We flow in helium and we flow in our reagents into this cryogenic environment at actually high temperatures. But before they have time to stick to the walls, they can form molecules. We shine a very powerful laser pulse for about a nanosecond. We create molecules at about, we create these plumes of atom at around 10,000 Kelvin. A millisecond later, you have already formed molecules and they start coming out. At around 5 milliseconds, this plume starts to come out, but it's pluming out. So we want to prevent it and collimate it. We shine some lasers at it, but actually more likely it's sending it into a laser maze. In the interaction with the laser maze, in about 20 milliseconds, this beam starts to get collimated and come out. And lastly, for this about 3 meters of travel, we shine a counter-propagating laser beam to it to slow it down. Once you've slowed it down, the molecular beam is bunched about 100 milliseconds later, and you can verify your slowing by shining a tiny laser beam to probe it and collect the scattered photons. We've made tremendous progress already in building the beambox. This is a model of the buffer gas cell. This sits inside of a vacuum chamber, and there are cryocoolers to cool down the cell. And turns out to shield this from the environment, we actually need cryogenic radiation shields. This is the beambox arriving in the fall. We had to get inside there and clean it. This is us assembling the cryocooler, assembling the thermal shields, dropping the shields inside the vacuum chamber. And this is the first cool down with us enjoying some Colombian chocolate. Maybe I'll tell you about one cool other trick, the imaging system that we've also made. Because we work with micrograms of radium, we have very low molecule numbers. So we have to have extremely sensitive imaging systems. We've done really detailed modeling of this beamline where you have molecules coming from one side, the laser beam perpendicular to that, and if a single photon from this laser beam scatters from the window or somewhere in this vacuum chamber and makes it back to your imaging system, you would not be able to distinguish between atoms and scattered light because you have such a sensitive camera. So to this end, we have built one of the darkest imaging setups that I know of with a 1 to 10 trillion scattered noise suppression. And this allows us to detect about 100 molecules in a fast beam or 1 molecule in a slow beam. And we've already tested this with barium. There's a lot more to do. For example, the infrastructure for safely dealing with radium-226. Or one of the brilliant students in our group, Derek, is leading an effort to slow down a beam of radioactive molecule going at around 150,000 meters per second in a buffer gas cell as well. But with that, I would like to come back to this slide and highlight that this is an incredible opportunity for discovery in an optics lab that is kind of small. It's only about 100 meters squared and with a budget of about $10 million. But this is extremely complementary to larger scientific efforts like the LHC. By discovering new particles, we are able to maybe justify and provide directions to large scientific efforts to go and build better colliders. And vice versa, efforts at LHC, for example, this new paper that came out only about a week ago, they tell us how we can actually look for CP violation or what molecules would be good to look at. So I think this is a very synergistic approach at a small scale with this large scale science. And maybe lastly, I'll told you about this personal lesson that I learned from the Shelter Island Conference, that nuclear physicists and AMO physicists should collaborate more. And to this end, along with my colleagues, we organized a technical workshop last year to bring this community together. And it's been wonderful to see the field grow exponentially even in the past few years. And with that, I would like to thank the wonderful RAX collaboration here at Harvard, MIT, and Caltech. Um, the wonderful alumni and the MIT collaborators. And lastly, I would really like to thank the Pappalardo Fellowship, because starting such a daring project in your postdoc is often seen as a little bit crazy. And I think I only was able to do this because of the comfort and the security provided to me by this fellowship. And with that, thank you so much. I would like to answer any questions.